Okay, we are going to finish up the sun and start comparing the sun to other objects. So last class period, I think the place that we ended up with, I'm pretty sure on this, was talking about the fusion of hydrogen to helium. So here is the figure that I spent most of the time at the end of the last class period, talking about. Now, looking at this, goodness gracious. Not sure who's been using this computer on my account, but somebody is besides me.
I can tell you it's not me.
Okay. So when you look at this, the process of fusing hydrogen to helium involves a net process of combining 4 hydrogens to produce 1 helium-4. Helium-4 meaning that it has 2 protons, the 2 pluses that are shown here, and 2 neutrons, the 2 blue things. Along the way, it's giving off these gammas, and that's primarily the energy we're receiving. Additionally, you have these neutrinos that are coming off. Based on the number of neutrinos, they calculated how many we should get, they measured, and they had a big problem. Remember that? What was the solution? Now we don't believe it's a problem. What's the solution?
Like the types of neutrinos, as they traveled through space, by the time they got to the Earth, it was the certain type of neutrino that it started.
Right. There are 3 types of neutrinos, and they discovered that the neutrinos can change from one type to another. And so they know they're producing the type we call the electron neutrino because it is produced in association with electrons. And that's what they were measuring. But if you have the 3 different types, then it actually all made perfect sense. And so in the end, they actually had more confidence than they would if they just measured and found it, because they found what they didn't expect. And then as they understood better, they discovered, oh, and it really should have been that. We just didn't know that yet. So our first question here, number 1, how can we calculate the mass consumed from the energy converted? Because we're converting actual mass into energy. So one of these equations is the correct equation for converting mass into energy.
I haven't been able to find my computer.
You can actually use your computer. I'm going to have to go on now, but we should have plenty. Just log in because the next one's also a clicker question. So you just go to the turning point, wherever it is that you registered, and log in. Okay, so our answers here were 100% said E equals mc squared, Einstein's famous equation about converting mass into energy. That's good. These equations are all meaningful equations. This equation is the classical equation for kinetic energy. This one here is for gravitational potential on Earth. And this is relativistic kinetic energy. Relativist. So they're all meaningful equations, but the correct one for converting between mass and energy was the E equals mc squared. You getting there, Aldwin? Because we are up to our second question. How is power related to energy? I was worried it wasn't accepting answers for a while.
Or what email I used.
Yo, hold on. Do you sign up to Google?
I can't remember if I used my Gmail or my student or what.
No, when you sign into Google.
Yeah, it just didn't say my password.
If you go to like say password, you can like find what your most.
I don't know, it just didn't say.
Okay, this one here, we didn't have as clear of an answer. So talk to the people next to you and see if you can agree with them. Max, go ahead and discuss with Aldwin. I know he's been trying to get this going, probably not able to.
Sounds right.
I put B, but I could be wrong. I'm sure it could be A.
Alright, just like this.
Right, because like the more powerful something is, it takes less time to do the same amount of work, and so that would be, I don't know. Yeah. So
I figured it out.
maybe.
Okay, are you logged in? Because I'm going to repull this, and I want you to be able to get credit here.
Okay, you know how I can do it?
I've never done it, so the answer is no.
No, I've never done it either, so I don't know.
Yeah, you put up.
Okay, so go ahead and answer again. I'm going to come back here and see if my computer expertise is a big deal.
How are you doing? How are you? Very Thanksgiving. Yeah. Very excited. Yeah. Yeah. It's crazy. It's crazy.
Yeah, I don't know.
I tried.
Yeah. Okay, we have, after discussion, a very small change. One person changed their answer. Now, I'm not even sure if we've talked about this before, but it's something that's in the common vernacular, and yet people are kind of hazy about what it is. And believe me, even in general physics, after we introduce it, come back a month later and they're like, power? Power is the rate in which energy is converted, or the rate in which work is done. So work is force times distance is the technical definition. But basically, if I were to come over and push Russell, the force I'm applying multiplied by the distance he moves is the work that I did. So if I push him, he doesn't move, which is what he was trying to do there. Then I do no work, right? If I push him and I push him 2 meters in 1 second, or if I push him 2 meters in 5 seconds, the work, assuming it's the same, well, I'm getting a little bit fuzzy on this, but let's put it a different way because it's easy. My brother and I, we had to go hoe parts of the garden when we were kids. Every day come home from school and we got to hoe 2 rows. And so it's basically the same amount of work to hoe each row, right? And so I would get out there and I would try to do as fast as I could because I wanted to go on and do something else. And so I would finish in like a half hour. And my brother would be like, I hate hoeing. And he would finish like in an hour and a half. We did the same amount of work, but it took me much less time. So, my brother tends to think, oh, I did more because I worked for, 3 times longer. But we did the same amount of work. It's just that I had more power that I put out because I did the work faster. So power is how quickly the work is being done or the energy is being converted. So we talk about the sun, the power is the rate at which energy is being converted. And we can measure that Because where does the energy end up going after 100,000 years? It leaves the sun as light, and some of it hits the earth. And so we can measure the energy leaving the sun, and assuming the sun is staying pretty much at equilibrium, that should be how much energy is being produced in the core. Using geometry, we take how much strikes a square meter on Earth, and we can calculate what the total leaving the sun is. And so then we know how much energy per second is leaving the sun. And we have a special word for that power. We call that power, so the correct answer, by the way, was this. We call that power, for astronomy purposes, the luminosity. Luminosity is, of course, how much light is coming out, but that light is the energy, so how much light per time, the luminosity is the power. The world's largest power plant is the one that China built. You might have read about them displacing so many people because they basically flooded everybody's farmland to make this huge, huge dam. And at its peak, it's supposed to be able to produce 22.5 gigawatts. And just to make sure we're all on the same page, it's not gigawatts. My son even found some website that said giga is acceptable. They even admitted it, making Back to the Future. No one on set knew how to pronounce gigawatts, and so they just guessed, and they guessed wrong and said gigawatts. Great Scott!
I mean, GI does say, but I get that.
You can pronounce.
Like, I can see where.
I mean, giraffe is one way.
I get where they made the mistake. Yeah.
In your field, GIF or GIF, right? The creator wants to call it GIF, and everybody else is like, you're
Don't listen
crazy.
to him. It's crazy. It's
No, but the first letter in the acronym begins with all these.
Yeah.
doesn't matter. It's
Not worth our time, but the creator of the GIF format is adamant that it should be pronounced GIF.
Yeah,
And he's
crazy.
He's wrong. We're all good at this.
He's a dang fool.
Okay, so let's look at this and just do the math problem that's on the page here. If this Three Gorges jam, thank you for, dam produces 22.5 gigawatts and it runs for 1 day, how much energy is that? And if we were doing it by fusion like the sun, how much mass would it be? So 22.5 gigawatts. How do I find the energy if I know the power? Since we define power is equal to the energy over time, then what's the energy going to be? The power multiplied by time. So that's going to be 22.5 gigawatts multiplied by 1 day. Well, 1 day is not my correct units. What units do I need there? I need it in seconds. So I'm going to multiply this by 24 hours, because that's how long a day is, and then times 3,600 seconds per hour. So I've got a calculator. I mean, you guys are not so much calculator friendly as general physics. That's true. So that's 1.944 times 10 to the 6 and 9, 15. So that's how much energy is produced by that dam in a single day. And that's a huge amount of energy. And so now we want to calculate from this how much mass the sun would have to convert into energy to equal that. And so then I'm going to use which equation? E equals what? So that means the mass is going to be that 1.944 times 10 to the 15th joules divided by 3.00 times 10 to the 8th meters per second quantity squared. Okay, the speed of light in vacuum is a constant. It's actually, here's the correct Correct value is 29979. That's a 9. 2458
Also, you rounded up to
meters per second. I rounded it. Yeah. So between friends, 1.944 times 10 to the 15th joules divided by 9.00 times 10 to the 16th meters squared per second squared. I squared 3 in my head because I got that kind of skill. Well, that is going to be somewhere along the lines of 0.2. Is that right? No. It's smaller than that. It's like 0.02.
Is there in grams?
It's in kilograms. I am trying to figure out how to use this calculator. Well, let's just do it the long way. If I did it right on this silly calculator, it's 0.0216 kilograms, or a mass equal to roughly the mass of this. It's not much mass, right? Considering how large the sun is, that would be nothing to the sun. What was that?
Fusion reactors are efficient.
Fusion reactors are extremely efficient, yes. So that was the goal here, is to see how much energy you have available to the sun there. So next clicker question.
You're playing out.
I didn't mean to mock you. Where do auroras occur? Wah, wah. Looks like throw me a bone, Connor. Okay. We had 0, 1, 6, 1, 2, 0. Okay. I am just going to go straight to Aldwin.
To the atmosphere.
Okay. He said ionosphere. What's your reasoning? Besides having the correct answer.
I mean, I don't have a reason. I just remember it from earlier when we were talking about the Northern Lights earlier in the semester.
Okay.
And you mentioned it was there.
Remembers that was what we said earlier. You're correct. Just for people who are paying attention, the things above the purple line are parts of the Earth's atmosphere. The things below are part of the sun's atmosphere. Yeah. Not any of those things. Where's the photosphere?
Isn't that the outer layer of the sun?
Well, it's what we call the surface. It's not the outer layer, because the outermost layer is the corona, but we don't see the corona.
I meant the surface.
The chromosphere, where's that fall? Just above the photosphere.
You can't see that with the eye, right?
Let me finish writing this so I don't mess up my writing. Photosphere. If you block the light from the sun, you can see it. In fact, if you block the light from the chromosphere, you can see light coming from the corona as well. But you have to block the others because it's much fainter. The chromosphere is called the chromosphere because it has a pretty pink color. And as we saw in class, what gas gives us that pretty pink color?
That was too long ago. I don't even remember what I ate breakfast.
Okay, so it was about 2 weeks ago, maybe less. It was hydrogen. the heliosphere, I think heliosphere just means the gas of the sun, like atmosphere on Earth. On Earth, which is the lowest of these levels? Which of these three? Troposphere. And that's where we have our weather occurring, right? It rains, it snows, and whatnot in the troposphere. And then, the stratosphere is above that, and then the ionosphere. So we saw in the video very clearly the coronal mass ejections interacting and exciting. I put oxygen here. It's not just oxygen. In fact, different gases give you different colors. So this green, I believe, is the green from oxygen. But if it's exciting nitrogen, you'll get a different color. So the colors are associated with the types of gas that are being excited. And those gases, different levels is actually where you're likely to have the different gases excited. So it has to do with the height as well. The solar cycle. Now, that video, once again, was a really good video, and it talked about the solar cycle. Approximately every 11 years, the sun goes through a solar cycle. And so you see that top one? That's called the butterfly diagram. Why? It kind of looks like a bunch of butterfly wings. What they've observed in the solar cycle is that early in the solar cycle, you have sunspots that appear somewhere out here around 30 degrees south or 30 degrees north latitude on the sun. But as you go through the solar cycle, the number of sunspots increases and they appear closer and closer and closer to the equator of the sun. And then you have a minimum, they all disappear, and it starts over. The lower graph is showing the count of sunspots. Notice this is going back to around 1850 or so. The next slide I show going back a lot further. I think I do. And so you can see that the number of sunspots here, it peaked out at about 0.2% of the sun, of the half the sun that you can see. Here in 1960, it was 2.5 times more sunspots. When the sun is having a storm, it looks like a dark spot. Why does it look dark? Okay, the magnetic field is keeping the gas, bloking, if you want to take the spelling on the figure I took from the textbook. It's spelled blocking without a C. Blocking the hot gas from coming up. So it stays cooler, depressed by about 2,000 kelvins. Still really hot, over 4,000 kelvins. But since the light it gives off is proportional temperature to the fourth power, it's about it's about, I think it was 20% as bright. I don't remember what the number was. But it's not nearly as bright because of, or maybe it was 1/8, I don't know, because of the cooler temperature. And so if it's cooler, you're going to get less radiation from something that's cooler, right? But when you have a sunspot, the region around it, right, that hot gas has to go somewhere. And so it comes up beside the sunspot, and you actually have more radiation that comes from the area around it than you lost from the sunspot. So you have a net more radiation when you have sunspots than when you don't. So basically, we can use the number of sunspots as a proxy to measure how much radiation we're receiving from the sun. More sunspots, we're receiving more radiation. So what do you think should have been happening to the temperature of the Earth if we go from back here about 1885, when it was at 0.2% of the area, out here ramping up, right? It does, looking at the peaks, it does a ramp. If you're ramping up the sunspots, what should have been happening to the Earth? What? Should have been warming up. Well, then what should have happened there from 1960 to 1980 or so? It should have cooled off because that took a big dump. But then we have this. So it came back up again, went down again. So we take this expectation and then we have to compare it to reality. I've got 2 or 3 slides on this before I continue with the reality. So you saw this in the video. The understanding is that all of this is caused because of differential rotation. The poles of the sun do one rotation in 34.3 Earth days. But the equator does one rotation in 25.05 Earth days. Pretty significant, right? So what does that mean? That means that you have different speeds of material, and as you saw in the video, that drags the magnetic field lines. And the video pointed out something our textbook doesn't. This effect also goes as you go in with depth. It starts going faster as well. So the magnetic field lines get kind of tangled up. And when they get tangled up, you have loops that come through the surface, giving us a sunspot where it comes up, where it goes back down. And here's where the gas is bloat because of the strong magnetic field. So we saw actual real photographs, much more impressive than looking at this in the video. So here, this is just filled with information. This, I probably spent 20 minutes looking at this and trying to rearrange it and whatnot. So let me point out what each of these graphs are. First, this graph here, the most telling one. This is the recorded history of sunspots. So we're starting back in the time of Galileo, moving forward, people counting how many spots there are in the sun. And what we have here is a period from about 1650 to about 1710 when there were no sunspots. People were looking for them. They were trying to count them. Think how boring it would be if you're, well, son, for the next 70 years, you're going to be counting sunspots, and you start counting and you go, 1. In the end, right? The sun was very dormant, we say. So what would happen to the Earth based on our expectation of radiation? Go ahead. Okay, well, not little to no, but less. And actually, we're only talking like maybe 2% less. But that's still less. And so temperatures on Earth should have gone down. Did they? I don't think I have a graph of temperature back then. Yeah, I don't have a graph of temperature back then. But they did. Temperatures on Earth went down, so people were ice skating on the Thames River, It would freeze solid out there. So, look at Big Bend Parliament. You can walk out there at the Thames, and they would have, bonfire on the river, not on the bank. So it was really cold. Why was it cold? Because the sun was not putting off as much radiation. But then you see it picked back up here, and the temperatures increased. Then we have this. This actually is called the Dalton minimum. Where temperatures once again dropped, and then it came out. And you can see here from 1900, this is showing average is what this line is. The average sunspots ramped up there until around 1960 or so. And so the Earth should have been warming, according to just a basic understanding. But then from 1960, well, we had a little dip here. Then it came back up. If you look at global temperatures, they follow that really nicely. This whole sequence going out to here is followed really nicely. But then let's look at recent years. There's a divergence. The prediction, if you look at the sunspot number, should have been some decline. The actuality was increase. And so that's the kind of data that gets people worried that man might be, potentially responsible for some of the heating. Now, here's some other information to look at. here is temperatures over the last, 150 years or whatever. 100, yeah. And you can see the general warming trend going on here, but it hasn't been constant. And in fact, in this region right here, there were articles written of alarmists who were scared that pollution was causing a global cooling and that we were going to be thrown into an ice age if we didn't stop polluting. Obviously, we understand better now than we did then, the science that's going on. But that alarmism makes me a little less sensitive to today's alarms. This graph here, remember I said we can use sunspots as a proxy for how much radiation is coming from the sun. This here, which for creationists is very important because it's looking at the atmospheric carbon-14. So this is telling you information you need for carbon-14 dating. And you see carbon-14 dating has those minima. You see the Maunder minimum? That minimum in carbon-14 in the atmosphere corresponds to the Maunder minimum here when the sun wasn't putting off as much radiation. Why? Because the carbon-14 in the atmosphere is created by charged particles. Charged? It's neutral. It's neutrons from the sun striking a nitrogen atom, being absorbed by the nitrogen atom, and then the nitrogen atom kicking out a proton. So that's how carbon-14 is made in the atmosphere. So if the sun is not sending as much radiation our way, it's also not going to be sending as much solar wind, hence it's not going to be creating as much carbon-14 in the atmosphere. And so you see another proxy. You can use the carbon-14 as a proxy for how much radiation we were getting from the sun as well. And it matches up quite nicely. But then if you look at recent here, you're like, oh, that is a really steep increase in the carbon-14 in the atmosphere, meaning that, we're probably, even though the sunspot number is down, that's up. Maybe we're getting more radiation, for some other reason, not just the sunspot number. I'm not giving you conclusive interpretations of this because I don't think there are conclusive interpretations. There are extrapolations and best guesses and fits to data, but nothing conclusive. Here's what's going on with the sun right now. I've mentioned this a few times. The sun appears to be going into a more dormant stage. And why do they say that? If you look at the current sunspot, you can see this sunspot here. Now, this is not percentage of area. This is the number of spots. But the number of sunspots is like half, well, a little bit more, but what it was the previous cycle. And their projection is this trend should continue for a while. And so, this could be our last solar cycle for our lifetimes. Probably not. I'm not projecting that that's the case, but it's a possibility, right? That's a really significant drop, and if it continues, you can see even their calculated projections are higher than the actual sunspots right now. So the sun is definitely doing something interesting. And this is one of those things where, in hindsight, we'll learn a lot, so that next time around we know more. But the sun is doing some interesting things here. And, I said here, might be expected to see a Maunder minimum type event. This here, the data is updated continuously. So I took the latest picture, which was compiled October 3. Okay, so it's not in real time continuous, but they're updating as much as they can. We already had Milankovitch come up in one of our homework assignments. This is where I like to talk about it because the sun is such a prime factor in the Milankovitch hypothesis or Milankovitch theory. Other things besides the solar radiation that play into Milankovitch hypothesis or theory, that is, that the temperatures on Earth, the climate temperatures, not your local here in Lincoln, but Earth-wide, depend on, number one, the activity of the sun right here. But you also have the Earth's precession, that is, remember, the North Star right now is Polaris. But in the future, Vega will be the North Star, and we precess around. And that actually has an effect on temperatures on Earth. You have the obliquity, which is the tilt of the Earth. It changes between 22.1, 24.5. That actually does match what's said in the video. I thought it was only up to 24. I think I said that during the video. 22 to 24 is what I remember, but 22.1 to 24.5. And so how much we're tilted, obviously the seasons are bigger the more we're tilted, so that's going to affect the global temperatures. The eccentricity of the orbit, how close to circular we are. Right now we're at 0.017, but it varies between 0.0005, pretty much a perfect circle, to 0.0607, much more oval than we are. All of these things play into what the global temperature will be, and historically it predicted very well. Right now it appears not to be predicting well, which once again says maybe man is complicit. I did not realize I had duplicated the slide. This is the picture from a year ago. You can see 2015. Moving on. Sorry about that. If nature rather than man is responsible for global climate change, what should we expect to happen to global temperatures in the next 30 years? Just leaving Aldwin out. Well, at least I got to ask him a question, you know.
Yeah, can I get credit for that one?
You do get credit for that one.
Can I answer this question out loud? Get credit for? Nah, it's good. I just think that's
Gabby and Jessica. All righty, we're all in. And we have 4, 1, and 5. Well, this is a good case for you to once again discuss amongst your nearest neighbors. What's going on here? Nothing to discuss? Okay, let's do this again. See if we came to a better conclusion or a worse conclusion. So everybody answer second time. Russell? You got an answer for me? Okay. Well, it changed a little. Daniel, clear it up.
Okay. So when we were going over the graph, it wasn't like they had a structure where they predicted it would go, and then like at the last part, it wasn't following the structure, and so like based on the fact that it wouldn't follow the structure, it was going up, but then I said I could see because it would be going down, because they kind of predicted different things and it wouldn't go off their predictions.
Okay. You remembered some good information and you did pick the right answer. The key for that answer, and I'll go to this one even though it's a year-old figure, is that we have a big drop in the sunspots, which corresponds to a big drop in the radiation the Earth receives from the sun. So if man is not complicit, they expect that the sun is going to go into a dormant stage and the Earth should cool. So by the time you guys are my age, this won't be a controversy. There will be, 100% of scientists will agree on one way or the other, that either man was complicit or wasn't causing global warming. If it cools off, then we'll say, yes, it was just, the sun was more active, now it's dropped off. But if it continues to get warmer, even if it stays at a constant temperature, that would indicate that it's something besides the normal Milankovitch action.
So you're saying the Chinese might not have made it up? Global warming.
I must have missed it. I'm sure that must be a political statement.
Yeah. That's what Trump said.
I would say what my candidate says, but my candidate is often wrong. But he's not a bad person, and that's why he's my candidate. Okay. I never said his name.
Yeah, we already know that.
Okay. I still never said his name. Now we're going to move on to how we know the distance to things. So knowing the distance to the sun, that's easy. We know the distance to the sun today because we simply can send radar to the sun. It bounces off the sun, comes back, we measure the time, and we can calculate the distance. So the distance to the sun is something that's very knowable. We can make a direct measurement. That's not the way people like Eratosthenes had to do it. They had to try to use geometry. And that was the one that he didn't do such a good job on. Was it Eratosthenes? Actually, no, I think it was the person's satellite is named for. Hipparchus. I think it was Hipparchus. Anyway, a second method for things that are farther away that we can't directly measure by bouncing something off of is called parallax. And parallax is simply using geometry. This was one of the arguments that was used by ancient Greeks for the Earth being stationary, because they said we should see the relative positions of stars move if the Earth is moving with respect to them. And here's an example of why. So I stand over here. Right now I see Gabby right behind Latifah. Then I come over here and I see Daniel right behind Latifah. Gabby's way over to the right. Why did Gabby move? Well, obviously she didn't move, I moved. And if I know the distance from me to Latifah, and I know how much I moved, then I can calculate how far away Gabby is by how far she appeared to move when I moved, just using geometry. That's what parallax is about. And so the Earth orbits the sun, and so as we orbit the sun, we can take sightings of star positions, and if we have a nearer star that we know how far away it is, and we have a farther star, and we see how the two move with respect to each other, we know our baseline, how far we have moved, simply by measuring from one side of the sun to the other. It's a distance of 1 astronomical unit from the sun to us here, 1 from the sun to us there, so that's 2 astronomical units difference in the baseline. And then just taking the relative angles, we can calculate how far away it is by triangulation. So that is a way to measure distances nicely accurately. This is just an example showing geometry of, if you were to stand on one side of the Earth, move to the other side of the Earth, if you know what the radius of the Earth is, you can calculate how far away the moon is by measuring the angle with respect to the horizon. But it's a lot easier to just use the direct method of shooting microwaves and having them reflect back. So let's get to, I just asked this question. Ancient astronomers did not see any stellar parallax. What conclusion did this lead them to? As they didn't see, as I saw Gabby move, they didn't see that happen as the Earth went through the seasons. So what did they conclude? My scale is off. I thought I had some wacky answers going on here. All right. I swear that can't be a 5. Oh, yeah, it is. 5041. And this one must be 0. I can't see it. So we have two conclusions that people here came with that. Either the sun is the center of the universe or the earth is stationary. Just anyone want to blurt out? Which conclusion did I say they came to? Their actual truth is they came to the conclusion that the earth was stationary because they should see parallax as it moves. Now we understand that the earth moves and we can measure parallax because we have nice telescopes with good resolution. They were using the naked eye, and with the naked eye they couldn't see stars move with respect to each other. But now we do, so they didn't observe parallax because they didn't have appropriate instrumentation for it. We observe it, hence we know the earth moves. And is a ball, believe it or not. I think that flat earthers believe, the universe is only about 100 times larger in distance from the earth. I don't know. They've got some interesting beliefs to try to justify everything. So here's how we actually use parallax measurements for Earth. We measure the angular difference in looking at a star from one side of the orbit to the other, and then we divide the angle by 2. So this picture doesn't show the bottom blue line. It just shows the half angle, and we call that half angle the parallax angle P. And so now we have a right triangle here. The baseline is 1 astronomical unit. And then this red line is the distance we're looking for. And using the small angle approximation, we can say that the angle is equal to, I don't remember where the 206.265 goes, if it's on top or on bottom. I think it's the distance, diameter over distance. Yeah, I'm going to screw it up if I try to write it out. I'm sorry, I usually actually derive it. But the distance is a distance of 206.265 astronomical units. The 206.265 is a conversion factor between angles divided by this angle, the parallax angle, that half angle. And since 206.265 is in that equation, we just identify and define 1 parsec is equal to 206.265 astronomical units. So what is a parsec? Parsec is short for I don't remember if there's 1 R or 2 in parallax. You could look it up. So parallax arc second. That's what a parsec is. Parallax arc second. So it's the distance away something is if the parallax angle is 1 arc second. 1 second of arc. Now what's a second of arc? We like to measure our angles in degrees. 360 degrees in a circle. 60 minutes in a degree. 60 seconds in a minute. So it's 1 divided by 60 divided by 60, or 1/3600th of a degree is what a second is, an arc second. And so a parsec is the distance away something is going to have if that parallax angle is 1 arc second. Why do we introduce this parsec unit for distance? Because it makes determination of distance trivial. If you measure that parallax angle, you instantly know the distance away. Just by taking the distance is 1 parsec divided by that parallax angle in units of arc seconds. So that's a way of measuring more distant objects. From Earth, we can measure somewhere in the ballpark of 2,000 objects that have a parallax angle, a measurable parallax angle made from Earth. But we have that Hipparchus satellite that is orbiting the Earth, doesn't have problems with the Earth's atmosphere. It's orbiting, so it actually, it's a little bit farther away than us, not much. And it's able to measure at least I think it's somewhere in the ballpark of 100 or 200,000 objects with parallax angles. So we can make parallax measurements of many, many objects now. Now, if you compare that to the number of stars in the sky, that's very few. But it's a large number of objects that we can get the measurements for distance using this parallax angle. But then we go further. Now, a quick calculation just to see if you're on top of your game. Proxima Centauri is the closest star to Earth. It has a parallax angle of 0.7687 arc seconds. How far away is Proxima Centauri? So you don't have to have a calculator. It's showing you the math for each one. So you just have to put it into the right equation. Oh, I'm out of time? I like this class, I could go on and on. Okay, Max. All right, because we're out of time, we had a variety of answers. This one here was the correct answer because the distance is 1 parsec divided by that parallax angle. So it's just 1 divided by the angle of 0.7687 in units of parsecs. Okay, have a great weekend. Enjoy the extra hour of sleep.